We have a lot to do tonight, so any questions before we plunge in and try to get through quite a lot, as I said? No? Ready to plunge? Here goes. Last time I was talking about the chain rule. So what I propose to do, given the amount of material that I want to cover, is kind of just not spend too much time on the theory and do a whole load of examples. That's my strategy, and I'm sure you won't complain. What, I always do that? Let's always do that. Well, sometimes the examples don't make much sense unless there's a little bit of theory. But you're right, you're doing the theory in class, so I don't have to do so much here. About the chain rule. Last time we looked at the first simple example. There's a bunch of variety, well, there's a variety of different chain rules, bunch of different chain rules. Depending on how many variables you have in the domain, is it of one variable, two, three, etc., and how many you have in the range. So we're talking about a function of another function, but sometimes it might be a function of many functions or many functions of one function. The first example, version 1, which we looked at last time, was w is a function of two variables, but each of which is a function of one variable. So the chain is like this. You start with t, you plug it into these two formulas, and you get both x and y. You plug those into f, and you get one number, which is w. So you've gone from 1 to 2 to 1. Okay, so it is a chain, but it's more complicated than a single variable chain rule. So w, you should be aware, is a function of t. Again, t is the originator, gives you x and y, plug those in, and out comes w. So it does make sense to write dw dt without the squiggly d's, because w is just a function of one variable. And what we saw is that dw dt, in order to see what it is, you have to differentiate f with respect to x, but then you multiply by dx dt. So as t changes, x changes by this ratio, and then f changes by this ratio times that. That's basically a very quick theoretical reason. That's just the dependence on x, though. So the formula is going to have something to do with y as well. So x and y both change, and this formula shows you the dependence on that. So rather than giving any examples yet, I'm going to state some of the other versions, and then maybe we can just do some examples and mix them up a little bit. If instead w is a function of three variables, each of which depend on t, then the formula is basically the same, except now you have the z dependence as well. So again, dw dt equals df dx, partial, times dx dt. Notice here, by the way, again, that's the partial derivative because f is a function of three variables, not just one. Whereas x is only a function of the variable t. So that's why I write the regular old d's. There is some method to this madness. You're supposed to get the correct shape of the d, the squiggly one versus the regular one. So that's the formula from above. The difference in this case is that you have a z as well. So there's no real difference between these formulas. In fact, this one reduces to this. This one reduces to this one if actually there is no z dependence in the f. Okay. Slightly more exotic is where you have, say, w is a function of three variables as before, but each of these variables now depends on two other parameters. So say x is a function of r and s, and y is a function of r and s, and z also is a function of r and s. Well, maybe in order to emphasize these functions, it's cleaner to write them as, say, f, g, and h. Because otherwise you get confused about these x's and y's. So let's suppose, actually, f, g, and h is a really bad idea, because we've got an f already. So I'm going to call them g, h, and j. Sorry about that. Okay, I've already used the f here. So let's map it out. you've got to have two parameters, r and s. If you know those two numbers, you can plug it into these three formulas here, and you get x and y and z. So you get three different numbers, which you then plug into this, and you get one number. So we've gone from 2 to 3 to 1. Okay, that's the chain here. So basically, w, actually, in this case, is not a function of one variable, it's a function of r and s. Again, we started with r and s, we found x, y, and z, and then we found w. So w you should think of as a function of two variables. Therefore, the chain rule is going to have two formulas. We're going to be able to find dw dr, partial this time, because w depends on both of them. So what should that be? Well, it's really very, very similar. It's just that you've got to realize that all the derivatives have to be with respect to r. So it's the same as this formula, but with t replaced by r. So as we change r, x will change it. So we have df dx, dx dr. We also have a y change, df dy, dy dr, and a z change, df dz, dz dr. The only difference between this formula here and panning up this formula here is that, well, r has replaced t, but these regular old d's have become partial because x depends not just on one variable but on two, r and s. And so it's basically the same formula, but there is one other difference in that we have a companion formula for dw ds. And it's exactly the same thing. df dy, dy ds, df dz, dz ds. Now, I'm pulling a bit of a fast one here because I should conceivably use the letters G, H, and J. So perhaps this x could be written as a G. It doesn't matter because x is G. The formula says x is G. To be consistent with the previous formula, it's kind of nice to keep it as x. But you understand the difference between x equals G of this. You know the derivative is the same thing, and you're very good by now at switching letters around and not worrying too much about x being this way. X could be G. You can switch letters around. So the point is that the chain rules all have the same sort of flavor. And of course, there's actually a chain rule for any number of variables becoming any number of variables becoming one. And they all have the same form. However many variables you start with, you'll have a different formula for each one. And however many variables the f function has, the last thing you do, you'll have a separate term for each one. So these are just three examples of chain rules. These are not the only ones. All right? They're probably the most common. But you have to be able to adapt to the general situation. All right? So, good. Anyone bring any examples of these things? Anyone have a problem of a chain rule that they'd like to go over? I don't want to spend too much time on it because it's really, you know, it's sort of fundamental in a way, and there are many other things to look at, but I will do one example. So no one brought anything in? Okay. Next week, you all got to bring stuff in, or else we're going to finish real early. I'll send an email about that during the week anyway. All right, so just look, for an example, suppose that we happen to have x is cosine a times b, y. Well, you know, I don't even want to write it this way. Let's write it a little more complicated. So suppose f of x, y, z is equal to x, y, z, the product of the three. So the question is, what is d dA? Actually, let's even write it like this. What is grad f with respect to the variables a and b of b cosine a, f of b cosine a? I don't want to bog down the notation. I'm sorry. Let g of a be, I'm sorry, be f of b cosine a B, AB. All right. So you could actually evaluate what G is directly by plugging that in. But instead of doing it this way, let's find directly, use the chain rule to find dG dA. Okay? So what we'll do is we'll use, it's actually a modification of that last formula that we looked at. We'll say, okay, well, G depends on A and B, fine. dF dx, understanding that this is x, y, and z, times d dA of x. So that's b cosine A. So it's the first variable, looking at how changing the first variable times the derivative, how this quantity in the variable changes when you change A. So then we also have to do df dy times d dA of just b, because b is in the second variable there, plus df dz times d dA of AB. All right, so now we just have some things to work out. What is df dx? Well, looking at the original formula for f, df dx is yz. Now we have to compute d dA of b cosine A. Well, we treat b as a constant, and the derivative of cosine is negative sine. So this is minus b sine A. As for this, dB dA, b is constant, so that's 0. And finally, df dz, well, the derivative of df with respect to z up here is xy, treating x and y as constant, and dDA of AB is b. So this is the correct answer. You didn't have any y and z's and x's anymore. You need to replace x by b cosine A, y by b, and z by AB. So y is b, z is AB, x is b cosine A, y is b, and then we have this other b. And if you simplify it all out, you get minus ab cubed sine A plus b cubed cosine A. All right, now as an exercise, make sure that you can compute dg dB. I'm not going to do it because it's very, very simple, but you should make sure you can do it. If you want me to check it, or you would like to ask me for help, then you may email me throughout the week. I'll be glad to answer it. All right, any questions about that example or any chain rule related stuff? No? Any questions from you on the video? Oh wait, that's stupid. All right. Email me if you have any questions. I'm happy to answer them. Now, there was one other little thing that popped up. You know, it's kind of just a curiosity. I haven't seen too many exam questions on it, but since it only take about 3 minutes to do, I might as well say that we can now revisit implicit differentiation from Math 103 or the equivalent as follows. So you may recall that when we were young and naive and didn't know multivariable calculus or partial derivatives, we would have some equation like f of x y equals 0, say x cubed y plus y squared cosine x plus 3 equals 0. And we would say, okay, find dy dx. That's a single variable problem, and you implicitly differentiate and you solve for dy dx. But we actually have a better way of doing this now. You see, the deal is that here, it's not obvious that y is a function of x. In single variable, it's assumed that x is the variable and y is now a function of x defined by this equation. But we sort of can think of this as also being, well, it's a function of two variables here, and this happens to be a level set of it. And so we actually can use the chain rule to give a simpler formula for this without going through the rigmarole of the implicit differentiation. So just in case it comes up, I'll show you the method, and then there's the formula at the end of it, which you could also just learn, although the method's kind of nice. What we do is we consider this to be f of x comma, y of x, y is a function of x, equals 0. And actually, x is also a function of x. It's a pretty dumb function. X of x equals x. Okay? That sounds pretty dumb, but you know, you can change x to t now and then change it back to x later if this confuses you. I kind of like this. X of x equals x, and y of x equals y, whatever y was going to be as a function of x. So if we use the chain rule in the form that is at the top of this board here, but instead of t I'm using x, then, and differentiate both sides with respect to x, df dx is equal to df dx first variable times dx dx plus df dy times dy dx. That's the derivative of the left-hand side. But actually, because f is always 0, its derivative has to always be 0. So we get this. And dx dx is 1. So actually, we have this equation, df dx plus df dy dy dx equals 0. And we can solve for dy dx to get the formula we're looking for. And I'll use the alternate notation because it's more compact. Dy dx is equal to minus df dx over df dy. But I'm writing an f subscript x. So I just solved for dy dx here. And that's the formula that comes out of the chain rule. And that gives us a more sophisticated way. So we can come over here, find dy dx not using implicit differentiation, using partial derivatives. Well, according to this prescription, we let this quantity on the left be f of xy. We let that be f of xy. And according to the formula, it's minus the x derivative over the y derivative. And we can just take partial derivatives now. The x derivative is, you differentiate this, keeping y fixed, and you get 3x squared y. Differentiate this piece with respect to x, and you get minus y squared sine x. And the 3 doesn't do anything. There's a minus out front from the formula. And now you divide by the y partial derivative, which is, treat x cubed, x is constant, so this is x cubed, 2y cosine x. And that's what the answer is. So you don't have to go through the trouble of doing implicit differentiation. But it's not a bad exercise just to go back to your 103 skills and just make sure you get the same answer. You'll see how it all works as well. You'll differentiate implicitly, and then you'll factor, and then you'll put one on the other side, and this is the factor, and this is the part from the other side. The minus is from putting it on the other side. So it's a good exercise. I just want to emphasize that when I'm writing dy dx, that's a different thing from df dx partial. It's a different thing. This is y implicitly as a function of x. F is a function of two variables, and these are partial derivatives. It's kind of nice how it all ties together. All right, any questions about that little snippet? All right, well now we've got to move on to more of the meat, starting to approach the real sort of questions that we're going to find on the midterm, which I think you probably care about. Okay, so moving on to section 14.5 of the book. Now the aim is to look at something called directional derivatives. Okay, so last time I imagine we have some function of two variables, and we looked at the partial derivative in the x direction as just being the regular old derivative, but just in one direction. And then the y derivative is in the perpendicular direction. But it does not tell you how the function changes in some other direction. So we want to be able to deal with all directions. So we have some function f, which I'm going to assume is of two variables at this point, f of xy. So at every point in the plane, we have some value, f. And what we'd like to do is say, how does this change when you head off in a certain direction, starting at a certain point? So the idea is you start at some vector, or some point in the plane, rather, x0, y0, and you could plug that in and find the value of the function there. And then you have some unit vector u going off in some direction, and you'd like to know what, if you just took the function as a surface above here and just kind of cut it along this line, what's its derivative at this point? How is the function changing in the direction of u when you start here? Okay, so that's the problem. It turns out it's not so bad if you define this del f to be a vector itself consisting of the partial derivative with respect to x, comma, the partial derivative with respect to y. So it's a vector that has in its components the derivative in this direction and the derivative in this direction. And from this two values, we're going to be able to find the derivative in any direction by using the dot product. In fact, here is the formula. df, oh, this should be small f's. I'm not using capitals right now. Sorry about that. These are little f's. Well, one's you should use at the beginning of a sentence a capital F. And okay, basically there's no difference between a capital F and a small f if you define the function. It's just whatever you want to call the function.
You said small f of x, y.
Yeah, I just put a capital F here by mistake. There was no capital F anywhere. It's all small. It's all small. My bad. All right. Okay, so what is the change in f? We call it df ds, and we got to tell some pieces of data that it's u and x0, y0. So this is a complicated notation to mean, and you need to know what it means. It means the directional derivative of f at the point x0, y0 in the direction of the unit vector u. So it's exactly this picture here. Think of it as its sort of temperature at different points as you're walking along. So I know how hot it is here. It might be hotter over there because there's a campfire. It might be colder this way because there's no campfire. But what if I walk instead of directly to the campfire, sort of along this way? Will it get hotter or colder? Well, if this quantity is positive, it'll get hotter. If it's negative, it will be getting colder. So it has some sort of meaning in that sense. Even if you don't think of heights of surfaces, think of it as temperature. Not a bad way to visualize it or understand it. And here is the formula for it. It is this derivative here, del f, evaluated at the point. So you have to, this means, remember, you calculate this and you plug in. This is plug in. It's a sophisticated notation. And so you compute that vector. This is a sort of tangent-y type of vector in a way, but you dot that with u. So it's this quantity dot u. Now, it sort of makes sense. If u is in the x direction alone, then it will be 1, 0. So if u is in the x direction, it would be 1, 0. And if you dot this, df dx, df dy, 1, 0, then the 0 kills off the df dy and you just get df dx, which is what you'd expect. If you start heading off along the direction of the x-axis, you get, would you believe, the derivative with respect to x. Same if you dot it with 0, 1. That would give you the derivative in the y direction. So if you start going in a hybrid direction that's sort of like, say, half x and half y, well, then the slope is half the x slope and half the y slope. If you're sort of more xy than y, say 2/3 x and 1/3 y or something like that, then sure, the derivative is going to be sort of 2/3 the x derivative and 1/3. Actually, 2/3, 1/3 is not a great example because u has to be a unit vector. And 2/3, 1/3 is not a unit vector. If you sum the squares, you do not get 1. So remember, if u is not a unit vector, you have to make it into a unit vector by dividing by its modulus, by its norm. So if we go in direction v, you have to let u equal v divided by the length of v. To find df ds. All right? So, I could do some computations, but maybe I'll save them for some examples from previous midterms. Just a little bit more theory that we have to understand then, having gotten this formula. So, I don't know, it's not, I didn't write it very compactly, but there it is. That's important. One thing we should just try to understand is what does this mean? What does this del f vector actually mean? And this is quite important actually. So it's very important. Suppose we take the surface z equals f of x, y. So we now graph the heights of these things, sort of like a graph of temperature, say, versus position. But it's got to be 3 dimensions because the position is 2 dimensions. So we got some surface here. Here's x, here's y. There's going to be something hovering over the plane. And it doesn't bend around itself. It satisfies the vertical line test as a function. So it can't be a hyperboloid of 2 sheets, for example, in this direction, because it'll violate it. So we have z equals f of x, y. We're going to pick a point here on the surface and consider, so let's say that point is x0, y, x0, y0. What I want to understand is this. What does this quantity evaluated at x0, y0, what does it mean? What does it mean? Well, according to this formula, if we were to take any unit vector, so imagine you're standing on this surface, okay, and you're walking up and down it. So but you can walk in any direction. You're standing at this point, and you can say, oh, I'm going to walk this way, I'm going to walk this way. Okay, I know there's a song that's... Okay, anyway, so the question is... I'm old. Which way are you... Okay, so certain directions you walk, it gets steeper. Certain directions you walk, it could get steeper in a negative way, in the sense that you could be going uphill, you could be going downhill. Certain directions might actually be flat. So think if you're on a hill, you could sort of go up, you can go down, and you can walk sideways, so you can go somewhere in between. So the question is, which way is the steepest upwards? Which way is the flattest, and which way is the steepest downwards? This vector tells you that information. It will give you a 2-dimensional vector, as in a direction, not up or down, but it will just tell you your heading, which way is the steepest. This tells you then which heading, as in which way to head, which is the steepest uphill slope. At x0, y0. Again, it doesn't give you the actual vector of the slope. Instead, it tells you the vector of which way the thing is. Now, the magnitude of this does give you some information about how steep it is as well. But the fact of the matter is that it's really the direction that's the nice piece of information that you end up with. Now, why is it so? Well, it's because of the dot product. If you consider df dot u, this is the directional derivative in some unit normal, along some unit normal. So suppose that we understand this as the size of grad f, the size of del f times u times the cosine of the theta of theta, the angle between them. So if I'm going to walk this direction, so that's sort of this heading here, if I'm going to walk this way here, this is going to be largest when f, the derivative here, and u are pointing in the same direction because of cosine theta. Right? The largest value of that is 1 when theta is 0. So basically, this quantity is going to be the biggest when the direction of u is the same as the direction of this del f. Okay, so if you walk in this direction, you get the largest possible value for this, is what I'm trying to say. This means that the change is the greatest, and that's why it's the steepest. Remember, the derivative tells you the slope. And so the slope of all the directions you could choose, the slope is greatest when the angle is 0, meaning that u is pointing the same way. And that is why, that's the justification of this statement. What if you go in the opposite direction? Well, there's the steepest way. This is going to be the steepest down, the opposite direction. Steepest downhill. How do you find the flat direction? Which way around, then, is the flat direction, as in the place where you don't actually change height, you're just sort of walking around the mountaintop? Well, it's the orthogonal direction. So any direction orthogonal at right angles flat. So in particular, a level surface is a flat surface of a mountain. A level surface, by definition, if you walk around it, you're not changing your height. You're not going up, you're not going down. To walk around the level surface, you have to always be orthogonal at right angles to del f. Okay, so this is the point of these things. Now, everything that I've just said, by the way, works in 3 dimensions as well. Everything works in 3 dimensions, except that the formula in 3 dimensions, you just have an extra coordinate as usual. So if f depends on 3 variables, you have df dx, df dy, df dz. So as an example of a problem, here's something from a previous midterm. It says that you're in outer space, and the temperature, for some bizarre reason, at different points in space, with respect to some coordinates, which don't really exist because of relativity, but never mind, some coordinates, the temperature is given by the mysterious function x squared minus 3yz plus e to the z. Again, for no reason in particular. Okay, so what you've got to imagine is that there's some origin that we've decided, and we're calling this x and this y and this z or something like that. And the temperature is different in different parts, and it's given by this formula. So if you know where you are with respect to these coordinates, then you know how hot it is. All right? Now, actually, it seems like there are certain values of this which can be a negative temperature. So that's cool if we use something like Celsius, but not so cool if we use Kelvin, which goes down to 0 and then kind of stops. So not worrying about such inanities. Instead, we say that there is a spaceship that's moving along some trajectory, which they've written gamma t and never used again. So we've got this spaceship flying through, and of course, the spaceship is experiencing temperatures that are maybe hotter and colder and hotter and colder. And then it says that at time t equals 5, the spaceship is at 0, 3, 0 and has a velocity vector v equals 5 minus 2, 4. So the question is, at that instant of time, is it moving to a hotter or colder area? Is it? So if you let it go a little bit, so it has a certain temperature right then at that instant of time. A short instant of time later, it's moved a little bit. Did it move to a slightly hotter or colder area, or maybe the same? Okay, so hotter or colder movement. It was written a little bit more completely than that, but there you have it. That's the gist of it. So actually, this gamma of t is useless, and time t equals 5 is useless. It doesn't matter if it's 5 minutes or 5 hours or 5 whatever whatever. It doesn't matter. 5 billion years. This is the thing that matters. So here's the spaceship. Here's where it's moving at that instant of time. Is it hotter or colder? And the problem is actually quite simple. What you have to do is calculate the directional derivative of t dt ds at the point 0, 3, 0 with respect to u, where u is the unit vector of velocity, v over the length of v. So we might as well compute this. 5 minus 2, 4. So it's 1 over root 45, 5 minus 2, 4. And if you really want to be clever, you can write that as 3 root 5. Maybe I should have just done that, because 9 is a factor. Anyway, the actual value of this number is irrelevant, as we shall soon see. Let's just compute this. dt ds, again, at 0, 3, 0, u, where u is that vector up there, is equal to the del t at 0, 3, 0 dot u. So we're going to need to find del t. So let's just say over here again, t, I've got to rewrite this because I can't see up that high and calculate at the same time. X squared minus 3yz plus e to the z. So its derivative is, just differentiate with respect to x, 2x. Now differentiate with respect to y. That's 0, that's minus 3z, and this doesn't affect anything. And now differentiate with respect to z. That's nothing. You get minus 3y plus e to the z. So now evaluating it at this point 0, 3, 0 means you just plug in x equals 0, y equals 0, z equals 0. And if you do that, x equals 0, you get 0. Z equals 0, you get 0. Y is minus 3, it is 3, so you get minus 9. But then e to the z is e to the 0, which is 1. So be careful of that. It's minus 8, not minus 9. It could make a difference. Probably not, though. Let's see. So according to what I just calculated, this directional derivative is 0, 0, minus 8. So that's actually the direction, by the way, that the spaceship should go to get the warmest. Okay, even without finishing the problem, I haven't touched the u yet. I just want you to understand, if you're sitting at the point 0 in the x direction, 3 in the y direction, and 0, the place which is getting warmest is due downwards, negative in the z direction. Okay, so that's where you would go to get warmer. What if, however, you go along 5 minus 2, 4, wherever this is? Does it get warmer or colder? Well, let's dot it with this u vector. Okay, this is just a constant, so it's going to come outside, 1 over 3 root 5. And it's just 0 times 5 plus 0 times minus 2 times minus 8 times minus 4, times 4, which is negative 32. So you see, this doesn't matter, because whatever it was going to be, it was just a positive number. Actually, the only thing we care about is the sign of this, SIGN. It happens to be negative, so that means it's getting colder. Question?
How will we be able to pull out that 1 over 3 root 5?
Well, I mean, this is just an abbreviation for, if you prefer, 5 over 3 root 5 minus 2 over 3 root 5, 4 over 3 root 5. When you take the dot product, that factor of 3 root 5 on the bottom will be a factor of each of the terms. So you can kind of pull out scalars all over the place. And in fact, it is a rule, which I'll just cram in here, that u dot lambda v equals lambda u dot v, for exactly the reason that I just said. So I'm just using that fact. We have another question.
Yes, with the 0, 0, negative 8, how do you know that's the way that it's getting warmer?
Question is, how do I know that this vector is the place where it's getting the warmest? And it's basically exactly what I said over there, except in the three-dimensional version. This del t is dot u is actually the length of del t times the length of u times the cosine of the angle in between. And that's always the same. But u could be any point, any vector, any direction, right? The direction that will give me the largest value of this is the one where the cosine is the largest. And cosine theta equals 1 only when theta equals 0, basically. So it's basically saying if you go in the same direction as this, you have the largest change, meaning that you're going to get the biggest. So that's the reason. It's exactly the same as it is in 2 dimensions, but there it is in 3. All right? But in this particular case, because the dot product is negative, the geometrical interpretation is this. The hottest is that way. We are going some way that makes an obtuse angle. Remember, dot products, if it's positive, it's an acute angle. If it's 0, it's right angled. And if it's negative, it's an obtuse angle. So there's hot, there's the coldest. And we are going somewhere like there. So if we were going this way, it would be the same temperature. Anything below it is hotter, anything above it is colder. And we're going slightly above. So actually the only thing that really mattered was the z-coordinate. The 5 and minus 2 didn't even come into it. Any way with a positive z-coordinate is going to be colder. Any way with a negative z-coordinate is going to be hotter. Now, it doesn't mean that if you go for a long way in that direction, it'll keep on getting colder. It just means a little way. Of course, the function will change. The derivatives will change. This direction will change. And so everything is very local. It's always like just an instant later. If you wait much longer, everything can change. Slopes can change. So that's kind of what I want to say about 14.5. And so I'll move on to the next section, which is a bit of a nice section there. So if you look at Math 103, you find that you do things like, well, you do tangent lines and how to find tangent lines to curves. And then you can find points of intersection of curves. And then you do linearization and differentials. And then you do the error in this thing. And these are like separate topics in Math 103. And you spend 3 or 4 weeks of them. Here's one little section, half a week, on all of these things in multivariable. Okay, so we're just doing analogs of these things, and I'm going to spend quite some time on this section here because there's a lot of scope for different problems. Okay, so the first type of problem that I want to look at is this. You have a function f of 3 variables. And you want to consider its level surface f of x, y, z equals c. Again, remember that as you change the value of c, you get different surfaces that don't intersect. They're like onion, layers of an onion. They don't need to be all the same shape. They can change shape, but that's what the level surfaces are. So for one particular value of c, you get some surface that need not be a function like it was in this case here. You could get some sphere or ellipsoid or any of the things that we looked at, or something more exotic. So it's just some surface in space. Doesn't have to be closed. Could be a hyperboloid, anything like that. All right. At every point, assuming that this is a differentiable function, we have the notion of a tangent plane. So in one variable calculus, we have a tangent line. Here we're looking at a tangent plane. This is quite an important concept for people on Earth, such as us, I think. Right? The reason being that the Earth is round, but locally it's flat. Okay? It's not obvious that it's round. That is because it is such a big place compared to us that it looks like everywhere is flat. But of course, as you go around the world, well, this is not the right shape of the world, but you get the idea. If you go to Australia, where I'm from, for example, the tangent plane looks like this. Here it looks more like this, and the point being that more or less tangent planes are important because that's how the world looks to someone who's very small compared to the surface. So the question is, how do you find the damn things? How do you find the tangent plane? And the idea comes from this exact concept that we were just talking about. The idea comes from that. The idea being that as you walk along the direction of del f, that is the biggest change. So it's actually not the tangent at all. See, if you walk along the surface, the value of f is constant. It's a level set. So it's flat. So this is the normal to the tangent. So this is normal to the tangent plane. Okay, and to be more precise, you've got to evaluate this at x naught, y naught, z naught is normal to tangent plane at x naught, y naught, z naught, assuming that that's on the surface. Okay, so that one piece of information is enough to find its actual formula, because we know how to find the formula of a plane with a given normal. And I'm just going to now apply that formula. The formula of a plane with a given normal then, so explicitly here is the formula. We've decided that it's this normal vector, so this is the n from before, that's the normal vector, dot x, y, z equals some constant, which I called d before. But that constant actually has to be the value of this formula y0, z0, because that lies on the plane. So without much further ado, the actual formula, I'll give you two forms. The one in the textbook writes it out in great gory detail, expanding this out to df dx, again evaluated at x0, y0, z0, times x minus x0, plus, this is now getting in the way, df dy evaluated at x0, y0, z0, times y minus y0, plus df dz evaluated. How am I doing this? I'm not doing this very consistently. Damn it. Vertical line, I'm using the sophisticated notation. Y minus y0 plus df dz, again, always evaluated at this point, z minus z0 equals 0. Okay, so that's the sort of that says exactly the same thing. Is that del f evaluated x 0, y0, 0, 0, dot the vector x minus x0, y minus y0, z minus z0 equals 0. And it's exactly the same thing. Those two formulas, it's just the dot product is written out in gory detail. So those are the formulas. But remember how to write in one variable calculus. Remember the point slope form is, you see terms like m x minus x0. That's just this, except that you also need a y slope and a z slope. So it's very similar to the elementary stuff. Obviously a little more complicated. All right. So that is the equation of a tangent plane. Now, I should give one variation, which is important. If the surface is not expressed as f of x, y, z equals c, but is instead written like this, z equals f of x comma y. You can turn it into this other form. So just write it like this. F of xy minus z equals 0. That's the same thing, obviously. Just subtracted z from both sides. And if you think of this as the function capital F of x, y, z, now I'm using a capital. If you think of this as a function of 3 variables given by that formula, it reduces it to the other problem. It reduces it to the other problem. The only thing is, of course, that we're always going to have df dz be equal to minus 1, because the only dependence on z is right there, and the derivative is minus 1. So that's just parenthetical, of course. You would just compute it anyway, and you would see that you get minus 1. But I just want you to understand that there's really no difference between this type of problem and the more general type of problem. You can reduce this case to that. All right, let's do some examples. But first, I wonder if anyone has any questions about this particular concept of the tangent plane. Yeah?
Since it's a level plane, or could you interchange the points if you had two?
So the question is, can you interchange the points? Tell me which points you're talking about, please.
Like, let's say you had 0, 0, 0, and 2, 3, 4. Could you?
As your x0, y0, z0?
Yes.
Yeah.
If you had 2 points on the,
Two different points, right?
2 different points on the plane.
Yeah.
And
Well, not on the plane, on the surface, on the level surface, right?
could you interchange those points, like in the formula? Let's say you have 0 as your x naught.
So the question is, how does it depend? Like, is there some flexibility there? And the answer is no. In general, different points will have different tangent planes, right? You can even see it from that picture, right? This point here has a tangent plane that looks like this. This point has a tangent plane that looks like this. In general, unless the surface is very special, two different points are just generally going to have different tangent planes. And it's going to manifest itself in this formula in not only here, when you plug this in, but also in this derivative when you compute it. When you compute the derivative and plug in that point, you'll get different values. It's a minor miracle to get the same plane. Although I have to say one of the examples I'm going to do, actually you do happen to get the same plane. So in general the answer is no, but it might be occasionally. Another question.
I understand how you go from the gory detail formula to
Yes.
the simplified one, but how did you go from the level surface one with D to subtracting the x naught, y naught?
Well, again, I mean, it's just sort of, okay, so the question is, how did I get from this to this? Bless you. So the idea is, if you know, in order to see how the theory of it works, you get this dot this is a constant. That'll give you that will give you any plane that is normal to that vector. But that's a whole stack of planes. The question is, which is the one that contains x0, y0, z0? So basically, if you put the d on the other side and factor it in a way, you could end up with something like this. So what is d here? Well, when I say factor, this is a little theoretical, so I'll just spend a few seconds answering it, but then I'll do an actual example. If you take a look at this, just to expand it to this. This is the same thing as this equation here. So I'm just writing this up. Okay, so the question is, do you believe this? I'm saying the right-hand side is the same as the left-hand side, but with these three quantities. Because if you subtract this, you could factor out the del f, and you get this equation here. Okay, so this is the constant we're looking for, and the reason being, when you plug in x0, y0, z0, it has to lie on the plane. So that tells you what d is. Just by plugging in x0, y0, z0, you get the value of d. But again, there's nothing different from what we had seen before when we just said the normal to a plane is this and it goes through this point. What's this equation? We did exactly the same thing. This is the only difference here. is that we don't know what the normal is. We have to compute it by finding the del. Another question.
Yeah, on the first part when we were talking about del f.
Del f, yeah.
It was somewhere that you could walk on the surface, but here it's perpendicular. So how has that changed?
Well, okay. So the question here is, it's somewhere you can walk on the surface. When I first did del f, I had it as a function of 2 variables. But then I mentioned the function of 3 variables, and I said, think of that temperature example. It's a function of 3 variables, and del f tells you the direction where it increases the most. So that means if you're standing on this surface and you go in the direction of del f, then the value of f, x, y, z is increasing. So it's not constant. If you walk along the surface, it's constant. If you go out of the surface, it will change. If you go into the surface, it will change. And it changes the most in the perpendicular direction. So everything, the tangent, well, the plane perpendicular to that is going to be the plane where it changes the least, as in it doesn't change at all. Although, of course, it is curved, so it's only a very local thing. But nevertheless, that's the idea. So you actually are moving to, if you go along that vector, you're moving to a different level surface. You're moving to higher level surfaces along the vector and lower level surfaces along the negative of that vector. But to stay on the surface, you have to go in the direction perpendicular, any direction perpendicular. All right, so anyway, we have a formula, and so we have some problems that we can now answer. All right. So consider this. This is from a midterm, fall 2004. And it says this. Consider the function. I don't have enough room there. So I'm going to look at a 2-variable problem and a 3-variable problem. All right. So actually this is from spring 2004. Let f of x, y, z be equal to 9x squared plus y squared minus z squared. So question 1 is sketch and describe the level surfaces, and there's 3 of them. F of x, y, z equals 9, 0, and minus 4. 3 of them. So we have.
Right there.
Sorry?
Those are the 3 level.
Yeah, so they actually wrote f of x, y, z equals 9, f of x, y, z equals 0, f of x, y, z equals minus 4. But I didn't feel like writing f of x, y, z 3 times. Much easier to say it 3 times. Okay, so anyway, but let's do that 9 first. We'll have 9x squared plus y squared minus z squared equals 9. We have to sketch that. Well, as we've seen, these sorts of things are hyperboloids, and it's a question of whether they have 1 sheet or 2 sheets. I always like to do the 0 one first when I recognize that. So I'm going to backtrack and change this to 0, because I feel like that's I know it's a cone. I know it's a cone. It's a cone whose axis is along the z-axis. The fact is, this is 3x all squared, so everything is squished by a factor of 3 in the x direction. But y and z are the same. So somehow it's a little fatter in this direction than it is in this direction. So it's an elliptical cone like this. So it's 3 times 3 to 1 is the ratio there. All right. So that's that level set. How about 9? The level set will be 9x squared plus y squared minus z squared equals 9. Well, this is now a hyperboloid of 1 sheet. Maybe we didn't need to do these all on the same axis, but I'll leave it to you. I mean, we've already done the surfaces. I don't want to spend too much time on it. You should write down the intercepts, and you can see that, for example, when you never have a z-intercept, because if x and y are 0, you can't solve that. But you'll have y equals 3 as one intercept and minus 3 and then the other one is x equals 1 or minus 1. Somewhere down here. So those are the intercepts there. The thing will be an ellipse, and as I said, it's 3 times fatter in that direction than this direction. And of course, at minus 4, you have a hyperboloid of 2 sheets sitting inside the cone, and the intercepts are at 2 and minus 2, as you can see by solving z squared equals 4. So I'll leave it to you to complete the details of that description, but as I said, we've already gone over that sort of ground. The real question is part 2, or part B I'll call it, is find to the one with 0, to the level set f of x, y, z equals 0, that's the cone, at the point 0, 5, 5, and also, so it's really tangent planes, also at 0, 1, 1. So, I don't know, maybe we should not take it for granted that those points are actually on the surface. The surface here, again, is 9x squared plus y squared minus z squared equals 0. So we should just do a reality check. 0, 5, 5. Does that even lie on this? Plug in 0, 5, 5. Yeah, sure. 25 minus 25. Same with 0, 1, 1. That's clearly going to lie on it as well. All right? So, I don't know. It's once in 50 years, we might try to fake you out by putting a point not actually on the level surface, in which case there is no tangent plane. Okay, what's the tangent plane to the Earth when you're standing on the moon? Doesn't make sense. All right, you have to actually be on the surface to have a tangent plane. If it ever happens, my guess is it's probably not a trick question, just we got screwed. But I've seen stranger things happen before. So the correct answer would then be there is no tangent plane. There is no tangent plane. Okay, now consider this. Some of you know what I'm talking about. All right, so let's do it. How do we find the tangent plane? Use the formula. We're going to have to compute, in general, this is f of x, y, z. By the way, if it wasn't on this particular surface, it would be on one of the level sets, because in this case, the level sets between all the different values you could choose over here will flesh out the entire space. You have the cone, and then all these different hyperboloids, like, you know, concentric almost, they're all stacked inside of each other, like Matryoshka dolls or whatever they're called. And then the same thing with these hyperboloids of 2 sheets, and together they kind of partition all of space. So every point is on some level set in this case. Now, however, you would just get a tangent plane to some other surface. Let's look at this case. We're going to need del f, in general, is the x derivative is 18x, the y derivative is 2y, and the z derivative is minus 2z. Very simple. Very simple. So at 0, 0, 5, 0, 5, 5, plug in 0, 5, 5, and you get 10. You get 0, 10, minus 10. So this means at 0, 5, 5, I'll use the sophisticated formula. I'll just write it out once for yokes. So in our case, this is the, just to clarify this is the x0, y0, z0. So I have to plug that in. The vector that I have was 0, 10, minus 10, dot x minus 0, y minus 5, z minus 5 equals 0. Okay, so you see how it works? I kind of took a working column here. I wrote down what f is. Hey, please. I wrote down what f is. I computed del f, and I plugged it in. And it's better to do it separately rather than you just plug it in directly. And then here I have x minus x0, y minus y0, z minus z0. And I just plug in those 3 points. And now I can do the dot product. 0 dot this is nothing, and I'll get 10 times y minus 5 minus 10 times z minus 5 equals 0. So you can divide by 10, and it turns out you'll cancel out the 5, and you get y minus z equals 0. And that's a plane. That is a plane. It's points where y minus z equals 0. All right. Its normal happens to be in the direction of 0, 10, minus 10. All right. Nice. We still have to do the other point, though. Okay. So the other point, we have, again, I computed this before, 18x, 2y minus 2z. And so at 0, 0, 1, 1, this is 0, 2, minus 2. So the plane has equation, I better write this out again, same formula, I just don't want to forget it. Okay, now I'm going to plug in 0, 1, 1. So I found that the derivative is 0, 2, minus 2, dot x minus 0, y minus 1, z minus 1 equals 0. And if you do this dot product as before, 0 times this, you'll get 2y minus 1 minus 2 z minus 1 equals 0. And you can divide by 2 and cancel out the 1s, and again, you'll find y minus z equals 0. Now, I don't want you to think, you had asked me, is it always the same? I mentioned that there is an example where they happen to be the same. That is a fluke. That is an absolute fluke. In fact, the question of part 3 says, explain, well, it says, are they distinct or not? Well, clearly they're not distinct. Clearly they're the same plane, since they have the same equation. The question is, how does this relate to the geometry of the level surface? So that's a sort of tricky question to answer. It's going to take some sort of diagram plus a nice explanation. See, we're sitting at a point on the YZ plane, so it's actually nice to have Y and Z like this and X sticking out, because then we can concentrate on the YZ plane. What's going to happen is that this level surface happens to be a cone, as we said. And here's the point 1, 1, and here's the point 5, 5. And in each case, the tangent plane is going to be y equals z, which is a plane sticking out of this board exactly like this paper here. It just comes straight out like this. So it's sort of hard to sketch because it's coming straight out. But this is the projection of this plane down there. And you can see that it's the same for both because they lie on the same line along the cone. So basically, you have to say, well, they lie on the same ray of the cone or line of the cone from the origin as shown in the picture. So the tangent plane is the same for both of them, and it is a plane that sticks out of the picture whose projection onto this is this. So you can just say the plane sticks out of the picture. It's really hard to draw, but you're going to have to come up with some explanation that is convincing enough to the person grading it that you know what you're talking about. All right? So I'm leaving you a little bit of work to do. It's not a bad idea to try to write down in your own words. Does everyone at least understand why it's the same plane for both points? Anyone not clear on that? I'm happy to sort of explain it again. All right. You're standing on the cone. What's the tangent plane look like? Well, if you walked up the cone, you'd be walking along this line. Okay, so imagine the cone looks like this now. Okay? And you walk up here. What's the tangent look like? Well, it's basically a plane that kind of pushes up against it. So it's going to be the same along every point on that line. It'll be over here, it'll be like this. And then it will come around and will always be tilted because the cone is tilted. But the point is that if you're on the same line going up, you have the same tangent plane. That's what we just want to see. So if you just say they're on the same line, because of the cone's shape, the planes are the same. So in this particular case, the plane happens to be coming straight out of the page. All right? So that was that problem. Another problem on the same review sheet, these are all online by the way, this is from sheet number 4, says this. Here's a two-variable problem. Let f of x, y be the function x squared minus 2x plus y squared. So first part is to sketch the surface z equals x squared, well, it's z equals f of xy. All right, so how do we do that? Well, that's the same thing as saying x squared minus 2x plus y squared minus z equals 0. And as we've seen, we've got to get some paraboloid. In order to see what it is, complete the square in x, add 1 to both sides, and you'll find that it's x minus 1 all squared plus y squared minus z equals 1. And we should recognize this as a paraboloid, which is ellipsoidal, elliptical, because these have the same sign. The reason it's a paraboloid is there's no z squared, but there is a z. So this is a paraboloid. We can sketch it like this. First of all, it's shifted in the x direction by 1. So its focus is at 1, not its focus, but its base is at 1 along the x direction. But otherwise, it's just one of these, it's elliptical. In fact, because there's no coefficients out of here, it's even circular. It's even circular. So it's a paraboloid with regular old parabolas, and the cross sections in this direction are just circles. So the description in words, circular paraboloid. You can call it elliptical if you like, ellipsoidal. Base 1, 0, 0. And you could write a little bit more, but that's again a sketching problem. The real question is, find the tangent plane at the point 1, 1, 0. Now, being naturally suspicious, I want to make sure that's actually on the point. If I plug it in, I get 0 plus 1 minus 0 is 1. Okay, fine, it's on the point. It's on the surface. So the question is, how do we find the tangent plane? Well, as per my description, you take this equation here, you might as well have it in this form, and you consider that to be your f. So I'm going to call capital F of x, y, z to be x squared minus 2x plus y squared minus z. And I want (2x minus 2), that's the derivative with respect to x, comma 2y, comma minus 1. So, again, as I said, you should always get minus 1 if you do this method, because you always have z equals something, you put it over here, it's always minus z, and the derivative is minus 1. So, when you evaluate this at 1, 1, 0, you plug it in, and you'll find you get 2 times 1 minus 2 is 0. Y is also 1, so we get 2, and z is always minus 1 here. So that's that. So the plane, I'm not going to write out the formula again. The plane has equation 0, 2, minus 1, dot, x minus the x-coordinate, y minus the y-coordinate, z minus the z-coordinate equals 0. And if you work this out, which I will do over here, you get 0 times x minus 1 plus 2 times y minus 1 minus 1 times z minus 0 equals 0. And simplifying that a little bit, you get 2y minus z equals 2. That's the equation of the tangent plane. Question? How is 1, 1, 0 on the surface? Well, the equation of the surface is x squared minus 2x plus y squared minus z equals 0. So I have to plug in 1, 1, 0 and make sure that it satisfies this equation. So when x equals 1, I get 1 minus 2. So I'm at minus 1. Plus y squared is 1 squared. So back to 0. Minus 0 is 0.
It's a problem
That's right.
So how can a point on the xy plane other than 1, 0, 0 be on the surface?
It's not on the xy plane. Wait. That's a... let's see. Where is 1, 1, 0? Did I draw this wrong? Doesn't look like I drew it wrong. Am I hallucinating? 1, 1, 0. Z. Oh, huh. Yes. Thank you. You are right. I have screwed up the sketch, but not the first part. Here is what I should have done. I should have brought the 1 back over here, like this. And therefore, the thing is shifted down also by 1. Thank you for that. I just lost points on my own exam. Actually, I'm not setting the exam, but embarrassing as it is, I should shift the whole picture down. Now, what happens? Thank you for pointing it out. So the base should have been 1, 0, minus 1. There you go. We should probably write down what the intercepts are as well in this case. They're not just obvious at all. I mean, you know what the base is. Where does this thing intersect the z-axis? Well, you set x and y equals 0, and you see that you have z equals negative 1. That doesn't seem to make much sense either. No, that's not true. Okay, now I'm not hallucinating. You set x and y is 0, and you see that z is 0. So this thing actually goes through the origin. So I should have drawn it like that. If you set y and z equals 0, you have x squared minus 2 equals 0, so the solutions are at 0 and 2. But when x and z are equal 0, y is 0. So basically, the only intercepts are along the x-axis at 0 and 2. So it goes through the origin. So that's a better description of it. So thank you for pointing that out, as I say. Still, I suspect this is correct unless I've screwed that up too, which is possible. All right, any other questions? Hopefully not pointing out mistakes, but yeah. Unless I've made all right. So there's a third part to that problem, but I can't do it yet because we haven't done the next section. But we will come back to it. For some bizarre reason, this is offending me because I'm going to talk about it soon, but I didn't write it. It's getting in my way. All right. Okay, so any other questions about finding tangent planes? I should mention that we can also find a normal line as well, but that's actually very easy. Suppose we wanted the normal line at this point. So what is the normal line? Remember, tangent plane, but normal line. So normal line at this point. This is not part of the problem, but I'm just going to throw it in. Well, if the tangent plane is perpendicular to this vector here, 0, 2, minus 1, which is del f, then the normal is along that line. So the line we're looking for, it goes through 1, 1, 0 along the direction of del f. This time it is capital at this point 1, 1, 0, which was 0, 2, minus 1. And again, how do we know what the line is? Well, the formula there involved a t, and it would you'd write r of t equals 1, 1, 0, the base point, plus some parameter t times the direction vector. This is just going back to what we've done before. So if you want to write it out, it's 1, comma, 1 plus 2t, comma, minus t. And for different values of t, that maps out a line. Okay, so make sure you can do that just in case it gets thrown at you. Again, this is no more than applying the geometry from the first part of the course with a little bit of calculus now. It's like using a point-slope form, but putting in the derivative instead of the slope. So you did the point-slope form in high school, when you did the derivatives in calculus, and you just apply the two together. All right. Bonzo. So, now I have to tell you about the tangent line to a curve of intersection of two surfaces, because it does sometimes come up. So suppose you have two surfaces. F of x, y, z equals some constant, and g of x, y, z equals another constant. They intersect somewhere. The intersection of two surfaces will actually be some curve. And so the curve has a tangent line. What is a vector tangent to the line of intersection of these surfaces at a point x0, y0, z0 on this line, on this curve? It sounds pretty formidable, but actually all it is, here's the surface 1, that's the F, equals C. Here's the other surface, G equals C1, and they'll intersect in some line. Well, what do we know about this? The tangent line is perpendicular to the normal of one surface as well as the normal of the other surface. So that the vector we're looking for, V, is perpendicular to both normals. Of course, the vector we're looking for, there's not one definite vector, there's just a direction. So any multiple of that vector is also a fair answer, except 0, because then that's just the 0 vector. So what we're looking for is the cross product, right? Given, if you have two vectors, the perpendicular vector is the cross product up to any multiple. So we need the vector we're looking for, V, which is the tangent to this curve, is equal to the normal to the first surface cross the normal to the second surface. That's the formula. Again, is it something you have to remember, or is it something you can work out on the fly? I suspect you should learn it. But it's the sort of thing where it's easier to learn if you understand what it means. You just try to memorize the symbols. I don't know. When I look at this, I say, cross product, we're looking for something perpendicular to this and this. Why? Because that's normal to the surface, and that's normal to the surface. Okay, it makes sense. All right, so here's an example from a final. It could just as easily have been on a midterm. You have two surfaces. Z equals sine x plus y cubed. And z equals 8. This surface is not very exciting. It's just a plane through 0, 0, 8, parallel to the xy plane. Okay, so there's some curve that lies at the intersection of these two, and you're supposed to find the unit tangent vector to that curve of intersection at 0 to 8. That's the problem. And my problem is that I'm not going to have enough room to do it right there. So. Is this going very quickly for you? Or is it really slow? It's sort of, as in, is time flying? That's what I mean. Are you having fun? Or is time just flying because it's just flying? I'm surprised at how late it is. I'm normally more tired than this by this point in the lecture, but what are you going to do? All right. Okay, this is not in the... Okay. I need to do more. This is not in the correct form. Neither of those surfaces are in the correct form. So let's just write the first surface as sine x plus y cubed minus z equals 0. And I will dub this fxyz. Equals 0. I could have written it still as z equals 8, but what the hey. And I will call that g. Won't make a difference. Okay, so I've got to compute del f. Well, del f I'll just do in general. This is cosine x, 3y squared minus 1. Fairly straightforward. And then, of course, I need this evaluated at this point 0 to 8. Cosine 0, of course, is 1. So I get 1, 3 times y squared, 3 times 4 is 12, minus 1. The value of z actually didn't come into it. Similarly, the del of g is pretty simple. It's just 0, 0, 1. And so that's true, of course, also at 0, 2, 8. It's constant. Doesn't really matter at all. The reason will be that if you do 8 minus z, then you will get the vector pointing in the opposite direction. Right? Now, the thing is, we're looking for a tangent vector to a curve. On a curve, but I didn't say what the parameterization is. I don't know. You're not walking one way or another. It's just a curve. So there's actually a tangent line. And so any vector along this line is an acceptable answer in principle. However, we're going to need a unit vector in the end, because that's what the question asked for. But there's still an ambiguity. Is it this one of length 1, or is it this one of length 1? I don't know. There's 2 acceptable answers to the problem so far as I can tell. And if you use 8 minus z, you'll get a negative here, which will give you the other vector. All right, so it doesn't really matter. In any case, we need the cross product. So the vector we're looking for, v, without the unit version of it first, is this is del f 0, 2, 8 cross del g, which, as we've seen, is 1, 12, minus 1 cross 0, 0, 1. So we bung out the old formula, I, j, k. This is a determinant, 1, 12, minus 1, 0, 0, 1. And the I is just 12. The j is negative 1. And the k is 0, if you work it out. So the vector that we're looking for can be rewritten as 12 minus 1, 0. Now that is a tangent vector to the curve, but we've been asked to find a unit tangent vector. So we have to divide v by its length, and you get 12 minus 1, 0, divided by square root of 12 squared plus 1. So that's 145. Maybe you can factor that, but what the hey. 12 over root 145. Comma minus 1 over root 145, 0. And again, minus this and plus this, which is what you would have got if you'd done 8 minus z instead of z minus 8, is an acceptable other answer, I suspect. I can't see why not. All right? So you see how, any questions about this particular type of problem? Just obviously make sure you can do it. Do some practice problems, but this is another thing you have to have in your arsenal of techniques, how to find tangent vectors. What if you actually had to find the line, the tangent line? It's very, very similar to this. But if you actually wanted the equation of the line, you wouldn't have to find the unit normal. You could just use the v. But just moving back over here, the line itself, r of t, equals the base point, which is 0, 2, 8, plus t times any tangent vector. So you could use the unit vector, but it's easier to just use the original one, 12 minus 1, 0. And if you want to write that out, that's 12t, comma 2 minus t, comma 8. Okay, so make sure you can write the answer in that slight change of the problem. Okay? So no other questions about that? That means we can go on to, well, I don't know, there's a little section on, I better do it. there's a little section on estimating approximate changes in certain directions. And I'm going to pull out the old spaceship problem again just to save some time. So suppose we have a function f. It could be of 2 variables or 3 variables. Okay, so you're anchored at a point x0, y0, z0, and you have a certain temperature. Think of this as the temperature. Okay, you move in a certain direction. With unit vector u. So the derivative, as we've seen, df, ds, the directional derivative at x0, y0, z0 in the direction of u is del f dot u. We looked at that right at the beginning of this class. Okay, so you can think of this then is if you go a short distance, ds in this direction, what this says is f changes by approximately this quantity df ds blah 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 times ds. Right? df is approximately, df is the change of f. So df is approximately df ds times ds. So in other words, i.e. it changes by an amount of this directional derivative dot u, which is a scalar, times the number ds, whatever that is. So in my spaceship example, we had a temperature which was given by x squared minus 3yz plus e to the z. And the spaceship is at 0, 3, 0, and the velocity was given by 5 minus 2, 4. Okay, so the question is as follows. I'm going to give you a slight different question. Okay, how much does the temperature change approximately? What is the approximate change in temperature? When spaceship has gone a distance of 0.2. units in this direction. So of course it doesn't actually go in that direction necessarily. It could turn away, but I'm looking for approximates here. Well, we had already computed that del t is 2x minus 3z and then minus 3y plus e to the z. So del t evaluated at this point 0, 3, 0. This is just duplicating what we did before, partly for practice, but it's mostly because I have no recollection of what it actually was. 0, 0, minus 8. Ah, yes, that rings a bell. Okay, so this is what we found before. So now we can work out df ds, or dt ds, at this point 0, 3, 0, but in the direction of u. Now, of course, u has got to be a normalized version of v. Now, I may have worked that out before. It was 25 plus, it was 45, right? So u, you might recall, was 1 over 3 root 5 of v. 5 minus 2, 4. And rather than write that out 3 times, I'm going to leave it as a scalar. We find that that is grad del t dot 1 over 3 root 5, 5 minus 2, 4, which is equal to 0, 0 minus 8. Hey, I'm just duplicating the exact computation that I did before. Never mind. I get, as I did, negative 32 over 3 root 5. Okay, well, I didn't remember that. Now I do. But what we want is the approximate change. Delta t is approximately equal to this dt ds at blah, blah, blah times ds, delta s. So maybe I should have written up here a delta s instead of a ds, but you get the idea. We just take this quantity, the derivative, minus 32 over 3 root 5 times the distance that we've moved, which is 0.2 of a unit. And this will be something like minus 6.4 over 3 root 5. Whatever that number is, that's approximately how much colder the temperature has actually gotten when we went in that direction. So you can see that it's colder because it's negative as it was before, but this gives you a sense of how much colder it is when we've gone this distance. So before we were just looking at the direction. Now we're actually considering the magnitude. The magnitude of this del F has some meaning. So I just want to make sure that here I'm using delta as change in. It has nothing to do with this del, which is the derivative operator. It's different. It's different.
Are grad and del the same thing?
Div, grad, curl, yeah, I guess. Does everyone call it grad F in class? Is that gradient F? Okay, I've been calling it del F. Call it grad F, it's the same thing. Div we'll do later. Curl we'll do later. Div, grad, curl. Grad F. In Australia, they say del F. I don't know, they say grad F. I've been to cities that never close down. All right. No one has a clue what I'm talking about. Anyone have a clue what that reference was? Okay, you have to Google it later. Now. All right. Next topic. Next topic. Yes, exactly. Linearization. All right. So in single variable calculus, the linearization at a point was simply the tangent line at that point. Here, it's essentially the tangent plane. I will look at the two-dimensional one first, and the three-dimensional is not much different. We have f of x, y equals, say, 0. I guess I want to be, well, I don't even care what it is. I just have a function, f of x, y, and I want a linearization. I want a linear version at the point x, 0, y, 0. So the geometric interpretation is that I have this function, which I could draw as z equals f of x, y as a surface. I have some point x 0, y 0, and so z is this point on the surface, and the tangent plane has an equation that looks like z equals L of x, y. And the idea, again, is that when I'm near this point, the tangent plane is very close to the surface. Again, if I'm walking in this direction, the Earth curves around. Hopefully the building doesn't too much. But if I was sort of on the Earth and the Earth was a perfect sphere, and I walk in this direction, there's not much difference to walking along the Earth than the tangent plane. And let's walk you a very long way, in which case the tangent plane goes off into space, and you hopefully don't. So basically, that's the idea here. We just need a formula for it. It's very similar. You can compute it exactly from what I just said and the previous stuff. I don't really have time to do it. It is in the book. But essentially, it comes out to this. L of xy. And I want to sort of emphasize, actually, that f is very close to it. So f of xy is approximately L of xy, which equals, by definition, first of all, you have the value of f plus the x derivative times x minus x0. By the way, in the single variable, that is the linearization. It's f of a plus df dx at a times x minus a. So this is the single variable. The two variable also has a y dependence. So this is a formula which you should really try to write on one line in your notes, because that's how you should do it. But I didn't have enough room on the blackboard. So this is a good approximation if f is differentiable near x0, y0. So when the point's close to that, the approximation is good. When you're actually at x0, y0, the approximation is perfect. If you plug in x0 and y0, these things go away, and you just get the value f of x0, y0. So it's perfect at x0, y0, and it's good near it. Okay, so the three-dimensional version just has an extra z term in it that's exactly as you expect, so I'm not even going to write it down. You should all write it down right now. What's the three-dimensional one? You just add on fz times z minus z0, except that now you have to put in each of these f of x0, y0, z0. So there's nothing much to that. Now, in order to give us an example, let's go back in the two-dimensional case to this problem. Well, it's gone from the board now, but this, we can now do the third part. We had this f of xy. This was the surface that I had a lot of trouble sketching, but the gentleman up there put me right on that. So we have x squared minus 2x plus y squared. So there's f. We actually consider the surface z equals f of x, y, but the third part just says, what's the linear approximation L at 1, 1? Well, according to the formula, L of xy in general is equal to f of 1, 1 plus the x derivative at 1, 1 times x minus 1 plus the y derivative at 1, 1 times y minus 1. So it's a coincidence that these are both 1s here. It's because the point is 1, 1. If the point was 1, 2, say, then this would be a 1 and that would be a 2. Okay, but as it turns out, we just need to plug in, well, we need to find the derivatives first. So here's f. We can actually plug in 1, 1. We get 1 minus 2 plus 1 is 0. Let's just come down here, take a little working column, and work out what fx is. It's 2x minus 2, and fy is just 2y. We kind of worked that out before as well. But anyway, if I plug in 1, 1, y value doesn't even matter, but the x value is 1, so we get 0. Whereas the y derivative is 2 times 1. So the linearization is pretty lame. It's just 2y minus 2. Doesn't have any x dependence. So that's all the problem asks. But the question is, what do you use the damn thing for? Well, what you do is, the question is, what's an approximate value of, say, f of 1.01, 0.98? Approximately equals what? Of course, you could plug in the number and compute it correct, like exactly if you had a calculator, or even by hand you could do it. But approximate value is just L, because this is close to 1, 1. It's just L of 1.01, 0.98. This is a very good approximation, which is easier to compute because it's just 2 times 0.98 minus 2, and that's much easier to compute. That's 1.96. So it's about minus 0.04. So without actually having to do any squares, you have this. And I don't think the book has any real examples of actually using the approximation. There's probably some exercises on it, but it doesn't seem to have any examples. All right, so that's the thing. Again, we're kind of rushing through it because you're assumed to sort of understand the one variable thing, and this is just an extension of it. I haven't even said a 3-variable thing, but I leave it to your imagination to imagine that there's a z thing in here as well and an extra term over there. All right, because I don't have time to do anything else. However, I must talk about the error. And this is a kind of contentious topic. So I like to spend a little bit of time on the error in the approximation. You know what? I think I'm going to skip it. I'll probably have to talk about it next week. I think I should use the next 15 or 12 minutes to go through the maxima and minima classifications and critical points, because I'm just going to be practical and say that the chances of getting questions of this form is just much greater than chances of getting the error questions. But next week we can, during the 4-hour session, we'll have more time to look at this. But I'd like to look at, okay, please bear with me. I can tell you a lot in 12 minutes. I can do all of this section, in fact, without any proofs. Okay. It all comes down to this. We're going to redo the idea of max and min, i.e. critical points and points of inflection, maxima, minima. And what it comes down to is this. A critical point was where the derivative vanishes, or as in is 0, or does not exist. That's in one variable. In two variables, if you have a function of 2, and of course this also can be extended to 3, but let's just concentrate on 2 variables. If you have a 2-variable function, f of x comma y, then the deal is this. At a critical point, I'm going to assume essentially that it's differentiable in general. A critical point has f of x and f of y either both 0 or one is 0 and the other does not exist, or maybe both don't exist. Those are called critical points. Now, normally what happens is the normal one we care about is when they're both 0. Or at least that's the interesting case. So, all right. We have this notion of local max and local min. A local max means that all the points in a little neighborhood around it are below the value. So x, y, I'm not even going to write it out. So we have a pretty good idea. Instead of looking like this, which is what it looks like, think of it as the bottom sheet of a hyperboloid of one sheet. That's the local max. You're standing on top of a hill. Now, of course, local, it doesn't have to be a global max. There might be a hill in the distance which is higher. But local means that while you're standing there, wherever you walk, you're going to go down. You're at the top of a little peak. Okay, local min is the opposite. It's the top sheet of the thing. There's the local min. However, we know we have, instead of points of inflection, we have these weird saddle points. And we've drawn these sort of things like this. So when you're standing here, if you walk in one direction, you're going up a paraboloid, so it looks like you're at a minimum. But in the other direction, you're actually at a maximum. So it's not really a top of a hill. It's sort of, if in one direction, it's the bottom of a valley, and in the other direction, it's the top of a hill. So it's sort of weird. It's a saddle point. Okay, so we're trying to classify these points. It turns out, again, you only get a maximum or a minimum or a saddle point at a critical point. That's the idea. So if you want to find the max and mins, you find the critical points, and then you classify them. Same as in one variable. So our program is going to be step 1, find critical points, and 2, classify them. Same as it was in one variable. Now, in one variable, we had this nice test using the second derivative. We saw that if at a critical point the second derivative is positive, then it's concave up, and so that point would be a minimum. If its second derivative is negative, it would be a maximum. And if the second derivative is 0, you can't tell. Well, in 2 dimensions, the situation is a little more complicated, because you don't just have one direction, and you don't know if the directions are sort of x and y. They could be in any direction. So it's a complicated test, or more complicated test. I will now describe it, and then I'll do an example of how to apply it, and I'll be out of time. So here is the nice classification test. Here's the analog of that second derivative test, using the second derivative. All right, here's what you do. Equals 0. So they both need to be 0 in this particular test. What you do is you compute all the second derivatives, f of fxx, fxy, fyy. You don't need to compute fyx because it's the same as fxy, at least if the second derivatives are all continuous. So in our examples, everything's going to be nice. You compute those three, and you put them in a matrix that looks like this. So the diagonals are fxx, fyy, and then these are the mixed derivatives, and these are the same. These are the same. And this is called the Hessian. This is called the Hessian. And actually what we want is the determinant of this matrix. So I didn't just put round parentheses, I put these lines here. This is the determinant here. And the test says the following. First of all, if the Hessian evaluated, this is, and you've got to evaluate this at the critical point. That you care about. So if the Hessian there is positive, you either have a local max or a local min. It's a local max if the second derivative in the x direction is negative. But it's a local min if the second derivative in the x direction is positive. So having seen that the determinant is positive, you just have to look at the top left corner. And if that's negative, you've got a maximum. Actually, you will find that if this is negative, then so is that. If this is positive, then so is that. So it doesn't really matter which corner you look at, you'll get the right answer. If, on the other hand, h is less than 0, you always have a saddle point. So there will be one direction, at least, where the thing is concave up, when you're facing that direction, trying to walk down like that, and there'll be some other direction where the thing is concave down, and you'll be completely confused as to whether you're at a maximum because of the fact you're at neither. Now, unfortunately, if h happens to be 0, then the test fails. It's similar to the test failing in the one variable case. Test fails. And there's no easy way to deal with it. What you have to do is actually explore the values around nearby. And unfortunately, that's not an easy thing to do in two variables because there's not just a left and a right like there is in the one variable case. So we're going to kind of ignore that and hope that it never happens. Of course it happens in real life. There are plenty of functions you can write down. But more or less, most of the examples I've seen do not have it. So please bear with me for another few minutes as I just do this one more example. This is from where is this from? Yes, midterm of spring 2003. It says find and classify the critical points of this function. All critical points of f of xy equals x times y times e to the minus x squared plus y squared over 2. Nice example. The first thing that I'm going to do to this, just for my sanity, is write this out actually as x e to the minus x squared over 2 times y e to the minus y squared over 2. So I've kind of split up this exponential, which you're allowed to do. But the beauty of this is that I can kind of differentiate with respect to just x or y and not worry about the rest. So the first thing is to find. So I'm going to need the first derivative in general. So I need to differentiate this. But if I'm differentiating with respect to x, then all this junk is constant, and I can just differentiate this, which is a single variable problem. If I use the product rule, I get v du dx, which is 1, plus u times the derivative of e to the minus x squared over 2, which if you compute it is minus 2x over 2, so it's minus x e to the minus x squared over 2. That's what it works out to be. It's all this junk times that y function, which I'm treating as constant. So if you work this out, this is actually, again, a factor, e to the minus x squared over 2. And so this will work out to be 1 minus x squared times y times e to the minus x squared over 2, e to the minus y squared over 2. And you could actually consolidate that if you want to be, well, let's just leave it. That's fine. Okay, so there's the first derivative in the x direction. Who can tell me, without even thinking, what is the first derivative in the y direction? No computation, please. Switch x and y. Notice that the function is completely symmetric in x and y. If you switch x and y, it's the same. So fy is 1 minus y squared times x times e to the, well, here, of course, I don't need to rewrite those in the other order. Excellent. So now to find the critical points, since the derivatives exist everywhere, we need fx equals 0 and fy equals 0. Well, exponentials are always positive. So the only way this can happen is that 1 minus x squared times y equals 0 and 1 minus y squared times x equals 0. So here you need x equals plus or minus 1 or y equals 0. Whereas here you need y equals plus or minus 1 or x equals 0. Now, if y is 0, then it can hardly be plus or minus 1. So if y is 0, x has to be 0. Right? You can't have y equals 0 and y equals plus or minus 1. Y can only be one thing. So if y equals 0, so one solution is y equals 0 and x equals 0. But if x is plus or minus 1, over here, y could also be plus or minus 1. So that's the other option. But that's actually quite a lot of points. So the critical points are 0, 0, 1, 1, 1, minus 1, minus 1, 1, minus 1, minus 1. There's 5 of them. And we have to classify all of them. Okay, I better finish this. I'm sorry. It's going to go just a few minutes over time. At least I'll classify the first few. Now, we need the second derivatives. So I don't really have time to compute them. All I can tell you is to get fxx, you take fx and split up the y's again, and instead of x e to the minus x squared over 2, you'll get 1 minus x squared of it. And it works out to be x cubed minus 3x y e to the minus x squared over 2 e to the minus y. Well, I'll write it as x squared plus y squared over 2. Fyy, once you've computed that, is y cubed minus 3y times x. I'm just going to switch them around. And actually, the mixed one is not so hard to compute. See, if you look at fx and now differentiate it with respect to y, you have this junk, 1 minus x squared e to the minus x squared over 2. But the y stuff is y e to the minus y squared over 2, which you've already differentiated. So you can sort of save time and see just by thinking about it that the answer is 1 minus x squared, 1 minus y squared, e to the minus x squared plus y squared over 2. All right, very good. So the Hessian in general, I'll just try to shoof through this. So the Hessian in general is you pack together these things, but I can't be bothered writing this quantity out every time, so I'm just going to take it out as a factor. This actually looks like this, x cubed minus 3x. Is that right? I just got to check that. I worked it out earlier. Was it x cubed minus 3x? Yes, excellent. So it's x cubed minus 3x, and then it'll be y cubed minus 3x, and then it will be 1 minus x squared, 1 minus y squared, 1 minus x squared, 1 minus y squared, and then there's also a harmless factor in each of these damn things of e to the minus x squared times plus y squared over 2. So probably I should have written it in each one. But if you think about it, if you have a factor here, a factor here, a factor here, and a factor here, when you compute the determinant, you'll actually get the square of the factor. You get lambda times lambda as a factor and minus lambda times lambda. So you'll actually get e to the minus x squared plus y squared. I'm getting a little fancy here, but you could have just written it into each of these things. Anyway, the point is that at 0, 0, which is one of our critical points, if I plug the damn thing in, this is just 1 anyway, and you get 0, 1, 1, 0. And if you compute that determinant, it's negative 1. So because it's negative, that's a saddle point. Let's just do it at 1, 0, at 1, 1. The Hessian is, I plug it in, I get minus 2, and also, there's a y here. I get minus 2 and minus 2, and these are both 0. So, and then I'll have also times e to the minus 1, as it turns out. So you can just double check that, but you're going to get 4e to the minus 1. Or is it e to the minus 2? E to the minus 2. So you get 4e to the minus 2, and the point is that that's positive. So you either have a local maximum or a local minimum. The sign of this is negative. So it's a local max. And just one more, although you should really check all three of them, I'll just do at minus 1, comma 1. The Hessian looks like this. You plug in minus 1. Well, something's gone way wrong here. This is what happens when you try to do things in a hurry. I'm so sorry about this. I was just trying to copy down this over here, and I left out the y. It hasn't actually changed the values of anything that I put down yet, but it does in this example. I plug in minus 1, 1. I get, actually, yeah, I get 2. And then down here, I get 1 minus that. So I get another 2. And here I'll have 0, 0 again. And so this time the Hessian is 4e to the minus 2. And you see that that's positive again, but now this is positive, so it's a local min. Anyway, I'm sorry, I'm out of time, so maybe I'll revisit this exercise next time. I would like to finish a bit quicker. But try working it out for yourself. Anyway.